In this video, I'm going to explain the following theorem. Let m and n be positive integers. If m and n are relatively prime, which is to say their GCD is 1, or another way of saying that is they have no common factor, then the group Z mod mn is isomorphic to the group Z mod m times Z mod n. And the map that's given by Z mod mn to Z mod m times Z mod n that sends a number a in Z mod mn to a mod m, comma a mod n is an isomorphism. So what this is saying is that these two different groups, on the one hand Z mod mn, which consists of the numbers 0, 1, 2, 3, all the way up to mn minus 1, that, from the perspective of a group theorist, someone who studies groups, is the same as the group Zm times Zn, which consists of ordered pairs, so it looks completely different at first glance, but from the point of view of a group theorist, they're actually the same, or isomorphic is the technical term. Let's do an example. So let's take the two numbers m and n to be 3 and 4. So they are relatively prime, in other words, they have no common factor. And this theorem is claiming that Z mod 12, the numbers 0, 1, 2, 3, all the way up to 11, with the group operation being addition, is isomorphic to Z mod 3 cross Z mod 4. The elements of the right-hand side here, Z mod 3 times Z mod 4, are ordered pairs. The first number in the pair is 0, 1, or 2, coming from an element of Z3. The second number in the pair is 0, 1, 2, or 3, coming from an element of Z4. And the group operation is component-wise. Now a non-example is that take m to equal 2, n to equal 4. So these are not relatively prime because they have a common factor of 2. And so this theorem does not apply. And in fact, the theorem isn't true in that case. In other words, Z mod 8 is not isomorphic to Z mod 2 cross Z mod 4. But it's not entirely obvious why. But here's the argument. Z mod 8 has an element of order 8, namely like the number 1. And Z mod 2 cross Z mod 4 has no element of order 8. In fact, every element of Z mod 2 cross Z mod 4 has order dividing the least common multiple of 2 and 4. The reason being that the elements of Z2 have order dividing 2, the elements of Z4 have order dividing 4 by a consequence of Lagrange's theorem, and so any element of this product, this Cartesian product, will have an order dividing the least common multiple of 2 and 4, which is 4. Now let's talk about the proof of the theorem. We want to show that this map F is an isomorphism. So let's try to remember what an isomorphism is. It's a function or map that's bijective on the underlying sets. In other words, it's injective and surjective. Injective means one-to-one, surjective means onto. And to be a isomorphism, we also need that F is a homomorphism. Let's check first that F is a homomorphism. Well, what does homomorphism mean? It means a function that when you do the group operation on two elements A and B, and then apply F, that's the same as applying F to the two elements A and B, and then doing the group operation in the target group. So in our case, F of A plus B is A plus B mod M, comma A plus B mod N. This is an element, this is an ordered pair, and so that's why it's an element in Z mod 3 times Z mod 4. Okay, and then one fact about modular arithmetic is that A plus B mod M is A mod M plus B mod M. That's a fairly simple fact. And so we can break up this component into A mod M and B mod M. Similarly, we can break up the A plus B mod N into A mod N, B mod N. And then notice that this term here is F of A, and this term here is, this term here is F of B. And again, the group operation on these pairs is component-wise. We add the first component here and the first component here, we add them together And that's how we got that component. Okay, now that we've shown that F is a homomorphism, let's check that F is injective and surjective. So here again is the map F. It takes an element A in Z mod MC and returns the ordered pair A mod M and A mod N. Now to show that F is injective, I'm going to use a fact that I'm going to prove shortly in an upcoming video. And that's a homomorphism F, any homomorphism, from one group to another group is injective if and only if the kernel of F is the identity element of G1. And this, well, what's the kernel? The kernel is the elements of G1 that map to the identity. So suppose we have an element on the domain side, so an element A here, that maps to the identity. In other words, it's in the kernel. What that means is that f of A is equal to 0, 0, because 0, 0 is the identity element on the target side here. And what we want to show is that this element A is the identity element in Z mod Mn. That identity element is 0, so we have to show that A is 0. So f of A, by definition, is A mod M and A mod N. And that is equal to 0, 0 is our hypothesis here. And so what this means is that A mod M is 0. That means that M divides A. Similarly, A mod N is 0. So that means N divides A. And now here's where we use the hypothesis that the GCD of M and N is 1. That these two facts, M divides A and N divides A, combined with the fact that M and N have no prime factors in common, means that their product, Mn, divides A. This can be deduced by looking at the prime factorizations of M, N, and A. So Mn divides A, and that means that A is equal to 0 in Z mod Mn. And so that shows that F is injective. Again, that's using this fact here, that something is injective, a homomorphism between groups is injective. You can check it by just computing the kernel. In other words, asking what elements on the domain side, like in this case Z mod Mn, map to the 0 element of the target side. Now that we know that F is injective, we can easily deduce that F is surjective, because these two groups, Z mod Mn and Z mod M times Z mod N, times Z mod N, have the same size. They're both sets of size M times N. And if you have an injective map between sets of the same size, then it has to be surjective. So that completes the proof of the theorem.